And we're back at it with Professor Ray, starting problem 1 in round 2. All right, let's work on this guy. A ball is dropped from the top of the tallest building in the world of height y1. What is the velocity of the ball, v2y, when it hits the ground? Okay, so it looks like we have our picture. It's pretty much drawn for us here, right? We have the coordinate axis. Let's get the spotlight, right? There's my coordinate axis. There's y equals 0. There's positive going up. Looks like I have my 2 dots here. y1 is up higher than y2 because you have something that's starting high, falling down. It says it's dropped. That doesn't say it starts at rest, does it? But it's implied. So when you have something that says you drop it, it means you start at rest, right? And then y2 is a little bit down here and has a v2y. Now, this is that question, right? What's the velocity when it hits the ground? It's not 0. That's why I have that v2y going downwards. That's the impact speed right there. And so over here, right, you can pick those two, right? You can always choose any 2 points, but for these 2 points, they have a physical meaning, right? y1, this is where, let me get the text out here so I don't have to, right? This is, let's see, top of building, right? That's your starting point, yes. But where are you? You're at the top of the building. v1y, right? So v1y, it starts at rest. It was dropped, right? So that's why we have v1y right there. y2, right? Where are we at y2? It hits the ground, right? That's what's happening here at y2, right? Just as a reminder, okay? This, right? This is the actual process going on, right? But we have to put that into a picture. And so, reminding, these have physical meanings. What is v2y? That's your impact speed, right? Right? y1 equals 0, right? That's we've chose that to be ground level, right? That's usually what you do. With free fall problems, ground level is usually where you put y equals 0. Does it matter? The answer is no, it doesn't matter, right? But usually that is. So where you put y equals 0, technically doesn't matter. We always make the positive direction up, right? Positive direction is upward. All right, so this is the process, right? Picture. Now we're on to the graphs. Give the graphs a try, and when you're ready, press the yes button. You've pressed the yes button. Hopefully you've given it a try. Let's go through this process one more time. Velocity. At time t equals 0, my velocity is 0. So I start at 0. Some later time, I always choose the farthest, right? I have a velocity that is downwards. Velocity downwards. That means it's negative, and it's bigger than what it was before. Right? So it's negative and bigger than what it was before. Take those 2 dots, draw a straight line. There you go. Now, acceleration. It's free fall. I shouldn't have to do anything with this, right? I could go through the whole process if I wanted to, right? But, boom, negative acceleration there. So acceleration is always negative. Okay, a few things here. If you want to speed ahead, you're welcome to before I get to the equations. 1, other ways we could do this. You're moving downwards, you're speeding up. Motion down, velocity down, speeding up. Acceleration must be in the same direction as velocity, so acceleration must be negative. Great. Slope of velocity time graph is negative and constant. Therefore, your acceleration is negative and constant, right? It's the other way you can do it. There's one other way that you can maybe think about this. When you're dealing with free fall problems, you know that your acceleration graph is always going to look like this. It's negative. What does that mean about your velocity graph? It means your velocity graph is always going to have a negative slope. It will always have a negative slope, right? Now, that negative slope, right? This is a negative slope. This is a negative slope. This is a negative slope. Those all have different meanings though, right? That's where drawing your initial point can be really helpful. I know initially I start at rest, so my initial velocity has to be right there, and that's going to tell me, boom, that is what my graph has to be, right? as long as you know one point, one little bit about how this works. Now, each of these has a little bit of a different meaning, right? This to me says that it would be dropped, starts at rest, like so. Okay. If I had something that was like this, that means it's moving in the positive direction and slowing down. That would be like me just throwing it up, right? Now, obviously, eventually it would stop and come down, but this is what we'd be looking at, just the upward motion to where it eventually stops, right? Still a negative slope, yeah? What's happening? Moving upwards, slowing down, velocity up, slowing down, acceleration opposite direction. Acceleration has to be negative. All these things work together. Let's see, alternatively, this would be, right, something that has a turnaround point, eventually turns around, speeds up. We'll see that again. This here, right, what's happening here? Starts with an initial velocity down. That means instead of being dropped, it's being spiked, right? Touchdown, Dr. Ray, right? Good job, guys. But now we are at a point where let's start putting the equations together. All right, equations here. Boom, boom. Let's see, this here is my velocity graph. So the area under the velocity curve is your displacement. So you get delta y is equal to 1/2 triangle times your base, which is your time, times your delta v in the y. All right, very good. Get to my acceleration. My area of the acceleration graph is the change in velocity in the y. All right, so I'll do that right here. Delta vy is equal to, now when I am going to solve this, I'm initially just going to put gt. I'm going to keep everything positive here, and I'll put in negatives when I need to, right? Sometimes it's easier to do it that way. Magnitudes, you get to the end, plug your negatives in when you need to. That's how I work through on these sorts of problems. All right, what am I trying to solve? Let's get that question mark, right? Notice I've drawn my picture, I've made my graphs, I've come up with my equations, and now I'm going to revisit the problem and be like, okay, what is the velocity of the ball, v2, when it hits the ground? Okay, so v2 is buried where? It's buried in this delta vy. So I'm going to solve for my change in vy. All right, there's two equations I can use for that, right? The bottom one doesn't have as many terms, one less term, but it's one less term. So do I know the value of gravity? I do. That's that 9.8 meters per second squared. Do I know the time? I don't. I do not know the time, right? Don't know time. So I go to the other one. I can already see this, right? I know a half. I know my displacement because it says that I started at height y and I hit the ground, right? But I don't know time. Okay, well, then, what do we do here? Well, guys, we make a substitution. We solve for time on one of them, we substitute it in, and we work from there. Not too bad, not too shabby. Okay, so what should we do? I'm going to solve for time. Right here, it's algebra. We'll end up at the same solution, whether you do one or the other. I'm just going to take the bottom one here, and I'm going to solve for time. So time is equal to delta Vy over G. Right, a little less to solve for, less to push around, right? Divide by G, G's divide out, and there you go. So then, change color. I take this delta V y over G and plug it into T. Okay, so I end up with delta y is equal to 1/2 times delta Vy over G. Sorry, that looks like a G. And then I have delta Vy. Delta Vy times delta Vy gets you delta Vy squared. So we end up with 1/2 times delta Vy squared all over G. Now I need to solve for this. All right, here's where some algebra comes in. Hopefully I'll be able to squeeze it in right here. Times by 2 times by g, right? So let's get a new color. There we go. So I take this side, times by 2 times by g. 2 divides out, g divides out. That 2 and g come over here. So you end up with delta vy squared is equal to 2g delta y. Right, how do I get rid of that square root? I have to do this. Oh, give you the answer. How do I get rid of the square? Gotta do the square root. And you end up with delta vy is equal to, what do we have? Square root of 2g delta y. Okay. From here, if something's under the square root, that means I gotta have something that's positive. So when I see g, I'm gonna put in 9.8. When I see a delta y, I'm gonna put in whatever my height is, right? My delta y. Technically, you'd have 2 negatives. Technically, we could put 2 negatives in. By that, I mean your delta y points downwards. Delta y would be negative, right? The value would be, because it would be y2, which is 0, minus y1. So that would be negative y1. And then g could then be negative 9.8 meters per second squared. So you get a negative times a negative. That, in essence, would work everything out. Or you could just say everything is positive and just go with it from there. Okay, I guess I'll do one more step down here. I have a little bit of room. So let's see. Boom. Okay, so I'm trying to solve not for delta Vy, but I want V2y, right? V2y minus V1y. But my V1y, I know, is equal to 0. So you end up with V2y is equal to square root of 2g times delta y. All right, we're going to do a unit check here, make sure everything works out. We have meters times meters over second squared. So you get meters squared per second squared, take that square root, and you end up with meters per second, which is exactly what we'd hope for velocity. Okay, so from there, you can solve all problems, right? Guys, just your mind won't be blown here, but you can solve all problems that are now just like this, right? Anything that you take and you drop, if you know that height, you're in good shape. And then you could just say, hey, my velocity when I hit the ground, when I just drop something, is just 2 times g times the square root of the height, right? So let's do it with a Logger Pro. Right, I'm going to take this, I'm going to erase, I'll clear it all and I'll just rewrite it, right? So we get v is equal to square root 2g delta y. All right, so motion sensor right here detects the motion however far away it is. I have this guy. I'll use this. I'll use my table. That way you can maybe kind of see things. And here's the ball. So the ball is going to come. I'm going to drop it. It's going to hit the ground, which is the table. Okay. There you go. But the thing is my motion detector, once things get too close, things don't tend to work very well. So I have to adjust how I take my data. So what I'm going to do is I'm going to put this on the ground. The motion detector by default says its location, right? Like where the sensor is located is the position 0, which is what we call ground level. So what I want to do is I want to make the table ground level. To do that, I'm going to 0 this. So I've come up here, experiment 0. You may not have heard that, but you might have heard some clicks. That was the motion sensor saying, all right, I'm going to set this distance that I see, which is the table. I put it under the table. It says that is now the 0 position. So now the motion detector is on the ground, it's not underneath the table, but right in front of me. So when I drop the ball, the motion sensor says that this right here is where 0 is. So now it's going to help me with my data collection. Okay, let's give this a try. All right, is that what we expected? I think so. I hope so. Let's see how it worked out. I want to mainly look at this part right there. So I'm going to auto scale just to there. Will it let me? Oh, I'll just zoom into right there. There we go. Ooh, look, that's -40. Let's make that a little bit slower, huh? Let's make this like -10. Okay, and I'll make this not all the way up to 50. I'll maybe make this 1. Okay, yeah, maybe a little bit better. I can make this even smaller, right? -5, right? -5. All right, getting some scaling here. All right, so a couple ways that I can look at this. It looks like I had a fairly stable height right here to start with. And then eventually, where did I start dropping, right? Maybe somewhere about there. What I'm going to do is I'm going to use statistics and say, you know, my average position was 0.78 meters. So about a meter, how about a meter above the table is what that says, 0.78. So if I started there, and then what I'm doing is when I hit ground level, right? My ground level is right here where I'm at 0. Come on now, examine. There we go, I'm right there at the 0. Pretty close, right? Position -0.017. Go over a little bit, 0.13. So this is pretty close to 0 right there. Okay, so that means how far did I fall? If I go right to the 0 point, I went about 0.7824 meters. That's your delta y. Delta y. Technically, your delta y is negative, right? Because you went downwards. -0.7824 meters. All right, what else do we need to know to get my velocity? And you know g. Now, I could put the actual value in for g if I wanted to, which would be -9.81 meters per second squared. And if I did that, how do things work out? So that's not a measured value, that's just a known value. So I take 2 times 9.81 times 0.7824, and that's 15. Hold on a second, don't forget to take that square root. Where is it? Square root. So 3.9. 3.9. So if I come up here and look at my velocity, okay, come on. I want to examine. There you go. Right about there. My velocity at that point is -3.86. 3.91. Right? So what this says, plug the numbers in, -0.3, oops, not 0.3, -3.91 meters per second. But the actual data down here, right? Now, when I say actual data, I mean, golly, this is pretty close, guys. -3.86. I mean, come on. It's like exactly the same. If I wanted to, right, say not use the calculated value for gravity, right? I could use down here, I have to look at acceleration. Ooh, man, talk about ugly, right? What's going on here? Right? What's going on? Where was this thing falling? Got to zoom out a little bit more, right? There's my position. This is when it's falling. And you can see it's definitely not as clean of a graph for the acceleration, right? But that's the part right there, right? Afterwards, all of this, that's where it hit the sensor and then it bounced away. So the sensor's making all sorts of funky readings. Acceleration is 0. That's when that ball is being held. Then you drop it. And this right there, what happens if I take the mean value? -9.42. Hey, you know what? That's not too bad, given the fact that it's a motion detector and I dropped the ball and it hit it right in the face, right? And it's not a very long one either. Do that, you're going to get a little bit off. Well, what would it be? Right, 9.472 times 0.7824 times 2 equals square root. Oh, you know what? When I use the actual value of that, right, g from the experiment negative 9 point, what was that? 472, right? Meters per second squared. We ended up with a velocity that was 3.84 negative meters per second. So, just saying, guys, works pretty good. Works pretty good. All right, gonna clear this. F3. Now, what do I have here afterwards? Got a whole blank sheet of paper here, right? Using the, well, Burj Khalifa building. I think that's in India. It's 828 meters tall, right? If you drop a penny, what's the velocity when it hits the ground? You're ignoring air resistance here. But I provide you the whole piece of paper so that you can eventually go back and try to solve this again as practice, right? You have the work right above, but if you can do this, read it, go through that whole process and answer it, that should give you confidence that you got it, right? But for the sake of this problem, you can just go ahead and plug in those numbers and solve it.